Good afternoon, everyone. My name is Moobum Kim, and I'm doing PhD in NTU. I'm very glad to talk about my research area in this conference. Today, I will talk about electrochromic alarm system with computer vision in smart contact lens. Here is the content. First, I will talk about recent research about the smart contact lens, and I will suggest the electrochromic alarm system, and I will show the electrochromic performance test. And also, I show the application of computer vision to electrochromic contact lens. Lastly, I will give the conclusion. First of all, I will briefly explain about recent research related to smart contact lens. Amount of glucose in tear is used for checking the diabetes. One of research group in UNIST succeed in detection of glucose in tear and wireless power supply and communication. And research team in KIST succeed in integration of solid-state lithium-ion battery with contact lens, and they check the performance of the battery. Also, research group in PostTech showed the glucose detection and drug delivery with micropattern. They integrated AES-IC chip for RF communication. For developing of contact lens display, curved liquid crystal were patterned on contact lens. They applied the voltage for changing the transmittance of the lens. In the previous research about smart contact lens, transmitting coil was used for data transfer and power supply. Vital signs from sensor in smart contact lens are very important for smart healthcare system. But for getting the data from the sensor, additional receiver at outside and complex circuit for data processing are inevitable. For solving this problem, direct information transfer to user by color change was suggested in this paper. For the color change, electrochromic material will be used with the voltage application. And the data can be transferred to the user directly by color change without additional receiver. For using electrochromic material in contact lens, there are several requirements. Safe to user, and using tear as electrolyte, and also easy patterning and fast color change with low voltage and economical material for mass product. Among the candidates, Prussian Blue was chosen for electrochromic alarm system. This material can be transparent and blue by voltage application. Here, we suggest the concept of electrochromic alarm system for smart contact lens. In the safe situation, contact lens maintain the transparent state, providing clear sight to user. But in an emergency, or when signals are needed to be transferred to the user, the color of contact lens becomes sky blue, so user can recognize an emergency and immediately react accordingly. For example, take a medicine or go to hospital. Electrochromic alarm system consists of the two Prussian Blue electrodes. One of electrode is located in the center of the lens, and the other electrodes surround the center electrode. If voltage is applied between these two electrodes, color of electrode can be changed. On the surface of the contact lens, thin film of Prussian Blue was electrodeposited on ITO and have electrochemical reaction with sodium and potassium ion in tear. Then Prussian Blue is reduced to Prussian White, which is transparent, and returned to Prussian Blue in oxidation reaction. First figure shows that well-deposited and patterned Prussian Blue on contact lens. University logo is clearly shown under the blue color. From this cyclic voltammetric curve, former potential of Prussian Blue were consistent with previously reported value in one more NaCl and one more KCl. In the mixed electrolyte, which has the same amount of sodium and potassium ion in here, two peak was observed and shifted to lower voltage as a result of mixed electrochemical reaction with low concentration. In third figure, Prussian Blue showed a clear color change between 0 volt to 0.5 volt. Maximum difference of the transmittance was 52.1%. For changing the color of Prussian Blue, 0.5 volt was applied between center electrode and surrounding electrode. For getting RGB data from the video, one frame was saved per each second, and then RGB data of pre-selected area were collected. Graph showed the average value of 100 points per each second. And red value changes 3 times more than green and blue value, and tendency of decrease in red value during color change was similar to decrease of the transmittance. So it is reasonable to use the red value in optical image to represent the color change instead of transmittance. And also diverse voltage was applied for 30 seconds, and bigger change of red value was measured with bigger voltage application. Also, by changing the duration of voltage application, the speed of color change was controlled. Let's see the video of color change. The video played 25 times faster, and duration was changed from 60 seconds to 7.5 seconds. Under 7.5 second voltage application, user can distinguish the clear color change. To demonstrate the brightness change of the vision, contact lens integrated with the alarm system was tested on the smartphone camera. The external camera will observe the color change of contact lens, and the smartphone camera recorded the scenery through the electrode on the center. Let's see the video. So clear color change was observed through the smartphone camera, and also average red value of 100 point in pre-selected area was collected, and trend of the color change in red value was same between the lens and scenery. Pattern color change of smart contact lens can be used for complex information transfer, such as vital sign or the result of image processing, as well as alarming function. Diverse pattern was demonstrated by controlling the time duration of voltage application with 15 seconds and 60 seconds. Let's see the video first. Color of lens became blue in 15 seconds, followed by transparent for 60 seconds, and 3 clear blinking of color change was generated. Also, 2 times of blinking of color change was generated 3 times. Also, Morse code pattern was made by controlling the duration of applied voltage. That was expressed by 30-second voltage application, and dash was expressed by 60-second voltage application. For demonstration, name of university and name of disease were transferred by Morse code. Also, direction was expressed by Morse code. Let's see the video. Left was expressed by L, and right was expressed by R of Morse code. For real-time application, if color change can be detected by camera of cell phone or laptop, user can do self-diagnosis in any time and anywhere, but user move the body continuously. So computer vision is necessary for detecting the position of color change and distinguish the kind of symptom. If user can detect the color change, different symptoms can be expressed by changing the number of blinking. For example, 2 times of blinking can express symptom 1, and 3 times of blinking can express the symptom 2. Computer vision is the scientific field deal with processing of digital image such as photograph and videos. Nowadays, computer vision is dramatically used for road and object detection, for self-driving car, and facial recognition. Also, some researchers used it for real-time pattern recognition for electrochromic microdisplay with temperature sensing. With the advantage of real-time recognition of moving objects and diverse patterns, computer vision was applied on electrochromic contact lens. Previously, MATLAB was used for getting RGB data in pre-selected area after taking video, but it was not real-time and needs fixed position of object. For processing the video using computer vision, Python and OpenCV, which is one of library of Python, were used. Capturing the video, data of 2D image which has RGB data at each point was obtained. RGB data of 2,500 points per each image were inspected, and if the difference of red value is bigger than 60 during 45 frame, that point was added to activated area. By processing the point of activated area, center point and radius were calculated. Finally, real-time graph of red value was obtained. Let's see the video. When there is a color change, computer vision detects the position of the color changing place, and when there is no color change, then nothing came out. In conclusion, clear color change of Prussian blue was demonstrated in same concentration of sodium and potassium ion of TR, and RGB value in pre-selected area was obtained using MATLAB by video processing. And also diverse pattern of color change were demonstrated under diverse conditions such as diverse voltage and duration. Clear color change was shown on top of cell phone camera and Morse code pattern was demonstrated. Finally, computer vision was used for video processing of electrochromic alarm system. It detects the activated area with a presetting of position, and real-time graph was obtained. And thank you to the Professor Lee about supervising me during PhD period, and also thank you to my group members, and they are very supportive to me, and we had a present time. And also thank you to the funding agency MOE and A-STAR. And also thank you to the KSEASG and KOFST for this AKC conference. Thank you for listening.